So the next chapter we'll be going over treats light as a wave. And in fact, we'll be thinking about light as a wave for a couple of weeks until the surprise twist at the end of this. If you know a little bit of quantum mechanics, it's not a surprise. That resolves the fact that sometimes we can treat light like a wave and sometimes like a shot particle or a ray. So what's going on, and the reason that light is such a peculiar wave, is at the fundamental level, it's really two waves. It's an electric field and a magnetic field, and the change in one makes a change in the other, and it kind of bootstraps its way and can even go through vacuum, which really baffled people in the 18th and beginning of the 19th century because all other waves need an independent media through which they travel. Rope waves need rope, water waves need water, sound waves need air or solid. But the electromagnetic field can do it for itself. And this is obviously a diagram. You don't see electric or magnetic fields as red and blue arrows. This is just indicating the strength of the field at this particular spot. So this doesn't indicate like the size of the electromagnetic field in any way, just giving an example of how the two bootstrap their way through space. And in fact, it turns out in short order after Maxwell's proof of this in, I think, 1864, all sorts of other branches of the electromagnetic spectrum were uncovered. So, in about 1800, people knew about infrared light by just misplacing a thermometer at the end of a prism after the red light, and the thermometer heated up. But then radio waves, gamma rays, and X-rays were discovered in short order, and eventually it was proved that these were all parts of the electromagnetic spectrum. The only difference in between any of these things is the wavelength of the light. So really long wavelength, microwaves and radio. Microwaves might be in between centimeters and millimeters. So the thing that you hold up to your head when you talk on the phone is basically a battery-powered microwave oven. Infrared, we give off infrared light when we heat up. There's a lot of ultraviolet coming from the sun. It doesn't make it too far through our atmosphere, which is kind of nice. And then X-rays and gamma rays, hopefully you don't have too much around you. They're generally made by really energetic things. So this is something like 20 orders of magnitude, and the visible light spectrum is really only half an order of magnitude. But the reason we don't notice this is, and you don't see light, a lot of the wave-like properties of light on a day-by-day basis is really because for visible light, the wavelength is so small. So again, 1/10 of 1/millionth of 1 meter is a typical wavelength for light. So what are the properties of waves? This might be partial review, but waves are disturbances that carry energy through space and time. So through all of mechanics, you're really just worried about point particles in some sense. So there's a dot, somebody told you it was an elephant or a trampoline or a toilet bowl being thrown out of an airplane. You basically treated everything like a dot. Can't do that anymore with waves, so they're delocalized. They move in both space and time, and as such, they have more properties that you have to keep track of. So here in between these two dots that are moving, so I won't mark them, you can see what's called the wavelength. So the wavelength is the distance it takes a wave to repeat. And I can look at these and read off of this moving graph that the wavelength for this wave is about 25 meters. So the other way in which a wave propagates is it changes in time. So the frequency is the number of repetitions per unit time. In SI units, that would be repetitions per second, or in units of 1/seconds or hertz. And the amount of time it takes to repeat is what's called the period. So in this case, I can estimate the period. So I think we'll wait until it gets to the top. So this wave gets to the top at 5 seconds. The next time this dot gets to the top, that would be the period. And then one of the two fundamental equations that describes what we could call wave kinematics is the frequency is 1 over the period. Okay, so that was 20 seconds, 1, 2, 3, 4, 5. So this has a 20-second period. It takes 20 seconds for one of these things to go from peak to peak, or alternately trough to trough at the bottom. So these are just kinematic variables, things that you keep track of for a wave. These are the two, this is almost definitional, but these are the two important fundamental relations. This in particular, the wave speed is equal to the wavelength times the frequency. This is like F equals ma for a wave. So it's really the most important thing that, for periodic waves, things that repeat, that you can remember. So once we get, that was a beautiful 1D wave, but even that one that was on the previous slide, we needed an animated image of some type to keep track of it. And the second you get into 2 and 3D, all of a sudden, especially on a chalkboard or a piece of paper, it's going to get really difficult to keep track of waves. And we definitely care about light waves in 2 and 3D. So this is just a plane wave, simplest wave you can imagine. And this is the plane wave being animated in 2D. So even 2D is kind of rough, let alone 3D with this weird multiple component wave that is an electromagnetic wave. So what we had on the last slide was a height, y, and it was a function of both position and time. So y was a function of x and t. But now in 3D, you can imagine that, ooh, we're in trouble. We've got to keep track of something, some variable, and maybe this would be, this wouldn't be y, this would be some amplitude, as a function of 1, 2, 3 spatial variables and 1 time variable. So gross. And in general, this is always true. Waves are a function of both space and time. So we have a couple of tricks to represent waves visually, and me animating stuff on the chalkboard will not be one of them. So you've actually seen wave vectors, you just didn't realize you were looking at wave vectors. So we'll depict waves by using wave fronts and wave vectors. So wave front is basically, if I were to look at the highest point of the wave, you could do it with troughs instead of peaks, but basically the maximum. So these lines indicate where the peaks of the wave are, the maxima. Imagine that you're looking down on it. This would be peak, 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 peak. Okay? So those are what are called wave fronts. So this circular wave, imagine dropping a stone in a still lake right about at this point, and these circular waves would ripple outwards. These would be where the peaks are. So those are the wave fronts. What the wave vectors are essentially what we've been calling rays for the past 3 weeks, 2.5 weeks, whatever. That's the direction of travel. So now I can represent this wave without an animated GIF in a way that you kind of know what's going on. These are where the peaks are. This is the direction of travel. So this would be the direction of travel of the wave where the arrow is pointing. This would be a peak. This would be a peak. And I could denote properties of this. So for instance, I know immediately that the wavelength of this wave is that. So that would be the wavelength. And likewise, this circular wave is spreading out in all directions. And I can tell that from the wave vectors. Okay. And if you want to be like really fancy about it, the length of the wave vector will tell you something about the how fast the thing is traveling. So we'll use these just as ways of depicting stuff. And this is, in some sense, how you combine some of the ideas of wave motion and the fact that you seem to get these rays that move forward and they don't bend or diffract, with the fact that light itself is a wave, and every wave I've ever seen, for instance, in a water wave, they spread out. And this is something, actually, this is sort of a schism in optics textbooks. Every other optics textbook you pick up will start by saying, Huygen's principle is the dumbest thing ever, and it just confuses people, and we're not going to use it. But honestly, it's pretty useful to understand diffraction. And what Huygens, who was a contemporary of Newton, realized is that, yeah, it's true that every point in space I could imagine making a circular wavefront and it would spread out. But the reason I get things that look like plane waves is because every point along the wave is acting like its own individual source. And when I start adding them together, I have 1 circle, 2 circles, 3 circles. The edges of those circles overlap and make what turns out to be sequentially a plane wave. So here's a picture of that where I have 3 point sources, and they would make a wave front that looks like this, kind of a very upright snowman. The wave vector would be this. These waves are traveling to the right, but then I try it again with 5 point sources. I get more lumps, so the lumpiness kind of evens out, and then more and more and more. So these are ideas that you know about from just general life. The more pixels you have, the smoother the image. So the reason people object to Huygens principle is because it's not like every point in space is really just sitting there making waves. It's just kind of a theoretical construct that you can consider a wave to be this, not that it really is. The reason to do this is because Huygen's principle and what he was trying to do was explain diffraction. The fact that if I have a barrier with a wave, so I've got a light wave coming in, and now you know what all these bits are. So the wave is traveling to the right, and these are where the troughs are, or peaks, I think probably peaks. And this would be the wavelength, the distance from peak to peak. And I block half of it, so I put this barrier here. Basically, I kill all of the individual sources, the so-called Huygens wavelets, when they strike this barrier. But this one on the far upper side, it no longer has these friends on the upper side to collaborate with to make a flat wave front. And so what you'll see, and you actually do see this, is the wave will diffract around it. So Huygens principle applied on the top and the bottom, I would cut off all of these wavelets where they strike this. I would get whatever the wave is coming straight through the gap, but then it would start curving around. And again, certainly with water waves you see this. We'll get to light waves and have an alternate description in a bit. And then finally, if I really squeeze this barrier down to the point where I basically have just one source, I would get circular waves again. So they would spread out. And the idea of waves spreading out around a boundary is what's called diffraction. Okay, the evergreen question, of course, is like, what on earth could we use this for? Why do I care? And we'll go over some of the wave kinematic formulas, the idea of speed and wavelength, and use Huygens principle and wave kinematics to get a wave derivation of Snell's law, which we had been using before. So in part, as a reminder of some of the properties of waves, we'll do a wave kinematics derivation of Snell's law. The other reason to do this is, you guys have been using Snell's law for quite a while now. Maybe we should determine whether or not we trust it. So same setup. I'll have medium A and medium B, or 1 and 2. Let's call it 1 and 2. And 1 is characterized by a speed. So speed of light divided by its index of refraction tells you its speed. And then we make it into medium 2, and medium 2 is characterized by speed of light divided by its index of refraction. So that's speed 2. And the difference is that I'm going to draw not just the rays or wave vectors, I'm also going to draw the wave fronts. And this kind of depends on how good I'm able to draw this, which right triangle I get to use. But let's just say, for the sake of argument, let's just suppose, because I got to draw something, suppose that V1 is greater than V2. So we're going from fast to slow. So if I'm going from fast to slow, stop and visualize what these wave fronts might do. And a good mental picture is that if you think about a whole bunch of cars driving at 60 miles an hour, and then all of a sudden the speed limit drops to 30 miles an hour, what's going to be true about the spacing in between this car, and this car? So that's exactly the right intuition. They bunch up. But what this means, because we're going to put numbers on stuff, and by numbers I mean symbols, is that the distance from this wave front to that wave front is the wavelength in medium 1. And what we're going to do is figure out what happens to all of these quantities like wavelength and frequency. Okay, so imagine that these wave fronts are coming in, they make it into this medium, they're going to bunch up. And the only way I can draw them bunched up is if they end up kinking, right? So this is the essence of Snell's law, and I'll draw that a little bit better. Is that the only way I get from big wavelength to small wavelength is if I draw something like this happening to the wave fronts themselves. So this is lambda 2. Okay, and really what we want to do is figure out what the relationship in between these and the speeds are, and then somehow an angle, a sine angle relationship, pops out in between that. So what we have is, and this will be helpful too, put our old Snell's law normal on this. So let's look at like right here. So here I have normal. And what I can do is perpendicular to these wave fronts, I can draw the wave vector or the ray. So that would be theta 1. And then perpendicular to that coming out, that would be theta 2. So basically, that's just geometry. We want to prove the sign relationship in between them. Okay, and so far we have the fact that these two aren't the same. There are a couple of other things that may or not be the same. So we have V1 is less than V2 just because to pick something. And just by looking at it, I know that lambda 1 is going to be greater than lambda 2. So the slower the medium, the shorter the wavelength, right? So I write that backwards. Yeah, V1 is greater than V2. If I said it wrong to you, ignore that. We said V1 is greater than V2. So lambda 1 is also greater than lambda 2. So the question is, what about the frequency? Frequencies for waves are extraordinarily high, so light waves. So a light wave in the visible or infrared spectrum, it might repeat 10 to the 15 times per second. So I'm not going to keep throwing around those crazy numbers. This is absolutely like not a light number, but let's just suppose that I have a wave that's repeating 10 times a second. Right? So 10 times a second, if I stand here and I watch this point, 10 crests per second will come by my finger. Every second, 10 crests. So my argument that the frequency stays the same is, imagine that I'm standing right here at the interface in between medium 1 and medium 2. So what's happening is 10 times a second, this wave comes and like knocks on the door essentially, right? So the frequency that it's beating here is equal to the frequency that it's oscillating at here, because essentially the thing that's making the wave oscillate in medium 2 is the fact that it's being, knocked or perturbed at the same exact frequency. If you're a mathy person, the other way of realizing that the frequencies are the same is that if they were oscillating at different rates, like the hour and the second hand of a clock, is that they would get out of sync. And you can't have waves do that. So one way or another, it turns out that this is true. When we go from medium 1 to medium 2, the frequency of the wave doesn't change. So now we have everything we need because we have the fundamental relationship for waves that tells us that V, it's true for 1 or 2, equals lambda f. And if we wanted to rewrite it, it'll be convenient to do this. So this would be true for 1 and 2. But because they have the same frequency, I don't need to put a subscript on that. And I can also rewrite this using the period. So this would be lambda 1 divided by t, the time it takes the wave to repeat. And again, for light waves, even in radio waves, this might be 1 billionth of a second, even for like a really slowly oscillating radio wave. Okay, so now we have all of the pieces that we need, and all that's left to do is a little bit of geometry. So here's the geometry. Let's see which right triangle I get to use. Let's pick on this right triangle. Okay. So this is perpendicular, and this is perpendicular. And this is perpendicular. So the wavefront is perpendicular to the wave vector. So if the thing's traveling this way, the line of crests or troughs would be that way. So that's a right angle and that's a right angle. It's clear to see from this one, which is why we're picking this right triangle. But it's also true for that one. So now I have two right triangles, one of which is in medium 1, the other one's in medium 2. They share this side. We'll call it H just because. And then I can just basically finish the proof by realizing that by examining the geometry, whoops, theta 2. This is theta 2, so those two open up together, and this is theta 1. So these are not similar triangles, but they share a side. So I have this right triangle that if I look at the sign, so opposite over hypotenuse, the opposite is lambda 2. So sine theta 2, and now we have sine of theta 2, so we're doing really well, is lambda 2 divided by this h. And I have the second triangle, sine of theta 1. So sine of theta 1 is this side. That's lambda 1 divided by h. And what I could do is I could rephrase them in terms of h and then equate them to each other. This is going to start looking like Snell's law. What this says is sine of theta 2 divided by lambda 2 equals h. And that says sine of theta 1 divided by lambda 1 also equals h. So basically we're like lambda 1. Let's do it this way. Sine theta 1 over lambda 1 is sine theta 2 over lambda 2. Voila, Snell's law. Which it really is, actually. It's just, the geometric optics useful version of it has nothing to do with wavelength, because again, the wavelength of visible light, is like super teeny tiny. So the last thing we're going to do is phrase it in the way that we want to using this information. So I want to maybe turn it into v, right? Because I know that v is related to n. So what I can do really quickly, and shame on me, crappy board work, I realize that for both of these, what's true is that lambda 2 is v2t, and lambda 1 is v1t, where that's the period. So I could rephrase this as v1t and call that v2t. Same frequency, same period. I can get rid of those. And what I'm left with is sine theta 1 over v1, sine theta 2 over v2. But then finally, what do I know about v1 and v2? Exactly how we defined the index of refraction in the first way. So finally, what we have is sine theta 1. So v2 is c divided by n. We have a 1 over 1 over, so n1 c equals n2 sine theta 2 over c. And just forget about those two c's, and you end up with n1 sine theta 1 equals n2 sine theta 2. Right. So again, the insight that's novel is thinking about waves getting crunched up as they go from fast to slow, and then how that must kink the wave vector, which we've been calling the ray for the last couple of weeks. And then the reminder that there's this wave kinematics that we get to use, and both of those are required together to make Snell's law.